Okay, so let's jump into our warm-up question. Start by saying proof. Let's say P of n be the statement. The sum I starts at 1 goes up to n of I times I plus 1 is equal to n times n plus 1 times n plus 2, all divided by 3. And we're going to prove this statement by induction. Hopefully that's not a surprise to anybody. So we want a base case. And we're going to have P of 1 is true because, so let's think about why. We sum up I goes from 1 up to 1 of I times I plus 1. Well, that's a very silly way of writing 1 times 1 plus 1. That's equal to 2. And 2 is also equal to 1 times 1 plus 1 times 1 plus 2 divided by 3, because I've got a 3 here and a 3 here that'll cancel, and I'll get my 1 times 1 plus 1. Can you use terms like left-hand side, right-hand side? Yep, fine with me. In this case, I don't think you're really saving that much. Maybe you could write right-hand side here, but it is important to know what you're talking about. So in this particular case, P of 1 means we have to put a 1 here. So if you just said left-hand side at this step, I wouldn't know you were talking about, because this has an n in it, this has a 1 in it. So I don't use them unless appropriate. If you're using them or I'm not using them, be careful, because you might be using them somewhere where they don't quite apply. Okay, my induction hypothesis. Induction hypothesis is let k be some number greater than or equal to 1, and assume P of k. And now we get to the induction step. This is where we gotta think about things carefully. So what is P of k plus 1 talking about? P of k plus 1 is talking about this sum from I equals 1 up to k plus 1 of I times I plus 1. Okay, so what is this? This is 1 times 1 plus 1, plus 2 times 2 plus 1, plus 3 times 3 plus 1, all the way up to k plus 1 times k plus 1 plus 1. But we want to use our induction hypothesis in here somewhere, which means we want to use the fact that if I only go up to k, the answer should be k times k plus 1 times k plus 2, all divided by 3. That's what P of k means. And the way I do that is by saying, okay, well, this is a sum. I'm going to add up all of the terms except for the last one. So this says start at 1, go up to k plus 1. This says start at 1, go up to k, and then stop, which means I've got one more term left over, which is the term I get when I plug in k plus 1. So that would be k plus 1 times k plus 1 plus 1. And I've done this so that my previous term appears, and now I can use my induction hypothesis. By my induction hypothesis, I know what this line is. This is k times k plus 1 times k plus 2 divided by 3 plus k plus 1, k plus 2. This is by my induction hypothesis. And now I just need some algebra. I have a k plus 1 and a k plus 2 in both of these that I can factor out. And what I'm left with is k divided by 3 plus 1. I combine this fraction, this is 3 over 3, I'm going to get k plus 1 times k plus 2 times k plus 3 divided by 3, or I can move that divided by 3 over here. And maybe just to really drive the point home, that is k plus 1 times k plus 1 plus 1 times k plus 1 plus 2, all divided by 3. So I have proven that the sum, if I go up to k plus 1, is equal to this thing that it's supposed to be equal to. Therefore, just get a new page. So p of k implies p of k plus 1. And by the principle of mathematical induction, I get for all n sum from I equals 1 to n of I times I plus 1 is equal to n plus 1, n plus 2 divided by 3. Or, in other words, for all n, p of n. How do we feel about that one? How was that for a warm-up? Questions, comments, concerns? Does it mean that all summations starting from I equals 1 to n, irrespective of f of x, would follow the same process? So I'm not going to make such a bold, large claim about all functions f of x, but certainly this is a common theme. If we're trying to prove something about a sum using induction, it makes a lot of sense to say, okay, well, when we get to our induction step, we're trying to prove something about k plus 1. We know something about k. We'll take off the last term, and then this will follow by induction, by our inductive hypothesis. We'll get from here to here. There are things we can do. I think there are some examples in the suggested problems where you have to pull off more than one term. You can't just pull off one term. We might get to an example like that today. I'm not sure. But yes, this is a good first idea to start with that you'll see come up again and again. Good question. Like that question. Okay, so I want to talk about a couple common errors that come up with induction. Yes, so just really quickly before I move on about the quiz. So while the quiz window is still active, you can't review any of your questions, but now that the quiz window has closed, you should be able to go in and see which questions you got wrong. Just while other people could still be taking the quiz. We don't talk about them. Okay. So I want to dig down into induction a little bit. In our induction hypothesis, PMI is principle of mathematical induction. Principle of mathematical induction. Which is just too much to write out every time, so we write PMI. Okay, so in our induction hypothesis, we are assuming that our statement holds P of k for one specific k. This is part of the reason why we switch from n to k. We make it clear that we're just picking one k and assuming it's just true in this one case. PMI works like this. For all k, P of k implies P of k plus 1. This is crucial. It does not work like this. This is the common mistake. You don't want to say, assume P of k for all k. This is a true statement, right? You can use the rule of universal specification to say if it's true for all k, then it's true for P of k plus 1. But this is not what PMI is. This is not induction. This is assuming everything is true, then one specific answer is true, which not especially helpful. So when we look at our example, we're picking a particular k greater than or equal to 1 and assuming that P of k is true. That is very different than writing something like, assume P of k is true for k greater than or equal to 1. So if you wrote something like this, that's wrong. You will lose marks for writing something like this. That is a different statement, fundamentally different statement than let k be greater than or equal to 1 and assume P of k. They look very similar, which is why I'm making a big deal about this. This one is good. This one is wrong. This one is setting up a statement that PMI can use for all k. This P of k implies this P of k plus 1. This is setting up this incorrect statement, assuming it's true for all k. It's true for one particular value. The whole point of induction is that in your inductive step, you're trying to prove your original statement. So if we look back, here we wanted to prove this statement, P of n. P of n is a very general statement. In our inductive step, we're trying to prove P of k plus 1. But that's the same thing. We're still plugging in a variable and trying to prove this thing. The only thing that makes it easier is this one additional fact. We have more information. If we just tried to prove P of n with no information, we just have to start with this sum and do some kind of analysis to get out this final answer. Right? We know our laws of logic. We'd have to use those to get to our answer. And that's hard. Well, our inductive step is trying to do the exact same thing with one additional piece of information, which is our inductive hypothesis. So, critically, second common mistake, make sure you're using your inductive hypothesis in your inductive step. Must use your inductive hypothesis in your inductive step somewhere. If you never used your inductive hypothesis, that means you weren't really doing induction. Okay. So, those are two common mistakes that hopefully you will now not make. And now let's just dig a little bit more into how induction works. So what do we get? If we've proven something by induction, we know P of 1 is true, and we know for all k, P of k implies P of k plus 1. Okay. So what does that mean? Well, let's say we wanted to prove P of n I want an argument that shows me P of n is true. Well, what does my argument look like? Well, I have P of 1, and then I can use the rule of universal specification to say P of 1 implies P of 2. And I can also use the rule of universal specification to say P of 2 implies P of 3. And P of 3 implies P of 4. And I can keep going, keep using my rule of universal specification until I get up to P of n minus 1 implies P of n. And this is my argument. P of 1 and P of 1 implies P of 2. By modus ponens, I get P of 2. P of 2 and P of 2 implies P of 3. By modus ponens, I get P of 3. P of 3 and P of 4, by modus ponens, I get P of 4. Keep going all the way down until I can finally conclude P of n. And that's where our concept of mathematical induction comes from. And this should lead to two ideas. Idea number one. Question? No? Okay. Idea number one is we don't have to start at 1. So if we look at this logic, if we look at how this works, if I wanted to prove P of n and n was some really big number, and I started at 3 instead of 1, I wouldn't know that P of 1 was true, I wouldn't know that P of 2 was true, but P of 3, P of 4, P of 5, everything after 3 would follow by this same logic. So let's take a look at that. Let's do an example with that. Let's say I want to think about 2 to the n versus n times n plus 1. Oops, there we go. Let's look at some values. Okay, if n is 1, this is 2, and this is 1 times 2 is 2, so they're equal. If n is 2, 2 to the 2 is 4. 2 times 3 is 6. So it's not true that 2 to the n is bigger than n times n plus 1 for all n greater than or equal to 1. Right? They start out equal, and then 2 to the n is smaller. You can keep going. 2 cubed is 8. 3 times 4 is 12. 2 to the 4 is 16. 4 times 5 is 20. 2 to the 5 is 32. 5 times 6 is 30. 2 to the 6 is 64. 6 times 7 is 42. And it looks like, at this point, 2 to the n is going to win. It looks like 2 to the n has gotten bigger than n times n plus 1, and it's always going to be bigger from now on. But I don't know that for sure, right? N times n plus 1, 1 was bigger earlier on. Maybe it'll be bigger again. So what do I want to do? I want to prove that this is true when n is bigger than 5. And I can use induction to do this. I can start my induction at 5. So let's do that. Proof. Let, using my notes. Let P of n, stuck with P it looks like, be the statement 2 to the n is bigger than n times n plus 1. And my base case, instead of starting with p of 1, I'm just going to skip right to p of 5 is true. Because 2 to the 5 is equal to 32, which is bigger than 30, which is equal to 5 times 5 plus 1. And now in my induction hypothesis, I want to assume k is greater than or equal to 5. Let k be bigger than 5 and assume p of k. So now in my induction step, what do I want to prove? I want to prove that 2 to the k plus 1 is bigger than k plus 1 times k plus 2. And I want to use somehow that 2 to the k is bigger than k times k plus 1. Which means I want a 2 to the k to appear somehow. So I'm going to force it to appear. 2 to the k plus 1 is the same as 2 times 2 to the k. And here I can use my induction hypothesis. 2 to the k is bigger than k times k plus 1 by induction hypothesis. And now I want to show ultimately that this is bigger than k plus 1 times k plus 2. So I'm going to take this k plus 1 out front, and I'm going to write times 2k here. And what I really need is, I need that this 2k is bigger than k plus 2. And we've got a good trick for doing that. This is equal to k plus 1 times k plus k. Get a new page. No reason to squeeze this in. And this is a nice trick because I know that k is greater than or equal to 5. So this step is greater than or equal to k plus 1 times k plus 5. Because I assumed way up here, k is greater than or equal to 5. So I'm using that fact in my answer. And now this is even bigger than k plus 1 times k plus 2, because 5 is bigger than 2. So I have proven that 2 to the k plus 1 is bigger than k plus 1 times k plus 1 plus 1. So p of k implies p of k plus 1. And for all n greater than or equal to 5, really important, since my base case was 5, this isn't true for all n greater than or equal to 1, it's true for all n greater than or equal to 5. 2 to the n is strictly bigger than n times n plus 1. I lost you at the k plus 5 step. Okay. So let's go back. So you're good here. 2k is equal to k plus k. What I want to get down to at the end, my goal is to get down to k plus 2. So I need to replace k with something smaller. I could go right to 2. It's just a little bit harder to see. What I know from up here is that k is greater than or equal to 5. So anywhere I see a k, I can write 5, and I get to get smaller. So I've replaced my k with a 5 because 5 is smaller, and then 5 wasn't what I wanted. What I really wanted was 2. But I know that 5 is bigger than 2, so that's fine. I could have gotten really fancy and replaced my k with a 2 immediately, but I think that's even harder to follow. So I threw in this extra step for you to try and make it make more sense. Okay. So that's one idea we can come up with. We don't have to start with 1. We can start with whatever value we want. The other important idea that we should get by looking deeply at induction is we can have more than one base case. Right, if we look at our induction, how it works before, what if we assumed P of 1 and we assumed P of 2 and we assumed P of 3? And then we started saying P of 3 implies P of 4 and P of 4 implies P of 5, right? And kept going. That's fine. All the way down until P of n. Because P of n minus 1 implies P of n. Something like that. So more than one base case, also okay. So those are two ideas we can get just by looking at how induction works. So we've been talking about a very simple version of induction where we always start with P of 1 and that's our only base case. But induction is more powerful than that. You can have any number of base cases that you want, and they don't have to start at 1. Now there's one more idea about induction that's a little bit less clear. And in fact, we give it a different name. So I want to look at that. So somebody is unmuted and we're getting some additional noise. I don't know who it is, but just check, make sure you're muted unless you have a question, please. So strong mathematical induction. Sometimes the principle is strong mathematical induction, but I like just the strong mathematical induction. SMI says we can even assume more. Just double check everybody, please, for me that you're muted. Getting a lot of noise through somebody's mic. Tried. Let's see. Mute all. Let's do that. Okay, so strong mathematical induction. Instead of showing, like we did in PMI, that for all k, P of k implies P of k plus 1, we can use all of our previous steps. So strong mathematical induction says for all k, we can assume P of wherever we started. So our starting value, S sub 0, and our next value, S of 0 plus 1. And we can keep going everything we've proven so far up until P of k and use all of that information when proving P of k plus 1. So this is using more information to prove what we want to prove. So let's do an example of this. Here's my claim. Every integer strictly bigger than 7 can be written as a sum of 5s and 3s. Okay, so let's do some examples. So 8, I want to write this as some 5s plus some 3s. I can do 5 plus 3. 9, how do I write 9 as a sum of 3s and 5s? Six plus 3 has a 6. 6s aren't allowed. Only 5s and 3s. You've got the right idea. There we go. 3 plus 3 plus 3. Good. So how about 10? Just using 5s and 3s. 5 plus 5. Very good. I like it. 11. How are we going to do 11? Good. 5 plus 3 plus 3. 12. What do we got for 12? There we go. We need 4 3s this time. And let's do one more. Let's do 13. How can we write 13? 5 plus 5 plus 3. Good. I like it. Okay. Now, if we take a look at these, there's a bit of a pattern. How did I write 11? Well, it was 5 plus 3 plus 3. What's special about that? Well, if I start with 5 plus 3, that was my strategy for 8. I took my strategy for 8 and I just added on 3 more. How did I get to 12? Well, I took my strategy for 9 and I added on 3 more. How did I get to 13? I took my strategy for 10 and I added on 3 more. So what's my strategy here? Well, if I know how to do a number 3 back, then I can do the current number that I'm working on. And that's something that regular induction can't do. The principle of mathematical induction, if I wanted to know how to do 13, I could say, well, I know how to do 12. But knowing how to do 12 doesn't really help you with 13. It's knowing how to do 10 that helped you do 13. You needed more information. You needed to go back further. So let's prove this statement using strong mathematical induction. So claim, or I guess I'll say proof, let Q of n be the statement n can be written as a sum of 5s and 3s. And now when we look at our base case, we actually need more than one base case. Our seeds of our proof, the fundamentals we're going to build on are 8, 9, and 10. Those are our 3 core ideas. So I want to prove 3 different base cases. Q of 8 is true because 8 is equal to 5 plus 3. Q of 9 is true because 9 is equal to 3 plus 3 plus 3. And Q of 10 is true because 10 is equal to 5 plus 5. Okay. So now our induction hypothesis is going to look a little bit different. We want K to be greater than or equal to 10. 10 is our last base case, so that's where we start our induction hypothesis. And we're going to assume not just P of K, but we're going to assume P of 8 and P of 9 and all the way up to P of k. So we get to assume everything we've done so far. And now in our induction step, we want to write, sorry, not P, Q, Q of 8, Q of 9, all the way up to Q of k. Sorry about that. I do mean Q, yes. Now I want to prove that Q of k plus 1 is true. But here's the thing, k plus 1 is equal to k minus 2 plus 3. And by our induction hypothesis, k minus 2, that's one of the things we assumed. Q of k minus 2 is one of our assumptions. So we can use the law of conjunctive simplification, the rule of conjunctive simplification, to just get Q of k minus 2. And Q of k minus 2 is some multiple of 3 plus some multiple of 5. This is equal to, let's say, 5 times A plus 3 times B. This is because of Q of k minus 2. And that means k plus 1, I just need one additional 3. So this is 5a plus 3b plus 3, which is equal to a sum of 5s plus a sum of 3s. So therefore, my induction hypothesis, Q of 8 and Q of 9 and all the way up to Q of k imply Q of k plus 1. So by strong mathematical induction, for all n greater than or equal to, now my induction hypothesis was greater than or equal to 10, but my base cases started at 8. So for all n greater than or equal to 8, I get Q of 8. Or Q of n, rather. So I'm using induction for any number bigger than 10, and my base cases cover 8, 9, and 10, which is why I get for all n greater than or equal to 8. Can I go back to my induction hypothesis again? Yes. So my base cases cover 8, 9, and 10. And now my induction step has to cover anything bigger than 10. So I assume I have a number that's at least 10. And I'm assuming all of these statements starting at 8. So I'm assuming 8 can be written as a sum of 5s and 3s. And 9 can be written as a sum of 5s and 3s. And 10 can be written as a sum of 5s and 3s. All the way up to, and k can be written as a sum of 5s and 3s. I'm assuming all of those statements all at the same time. Regular mathematical induction, PMI, would just assume P of k. It would only assume the last number can be written as a sum of 5s and 3s. But since I'm doing strong mathematical induction, since I want to jump back 3 steps to k minus 2, I need to assume more. And I'm just going overboard. I'm assuming everything, because I might as well. I'm assuming 8 is true, and 9, and 10, all the way up to k, compared to just assuming Q of k. Hopefully that one makes more sense. Okay, so this is strong mathematical induction. We get to assume more than regular mathematical induction in our induction hypothesis. We get a stronger induction hypothesis, more information. Okay, so let's take our break, digest strong mathematical induction a bit. We'll come back and start with a new idea. But let's say 2 minutes. So from 9:12, we'll start again 9:14. Go ahead, get up, stretch, grab a snack, watch a TikTok, whatever it is you got to do. We'll come back and refocus. Sure, the step that follows the conjunctive simplification. So I want to find a way, to write k plus 1 as a sum of 5s and 3s. And I don't know how to do it for k plus 1 yet, but I do know how to do it for k minus 2. So I have this big conjunction, 8, 9, 10, all the way up to q of k minus 2. All the way up to q of k. But the only one I end up needing in this case is k minus 2. So what I need is q of k minus 2. Q of k minus 2 tells me how to write k minus 2 as a sum of 5s and 3s. That is our jump back 3 steps moment. If I want to know how to do 12, I jump back to 9. If I want to know how to do 13, I jump back to 10. So that's our go back 3 steps moment. Why do I know how to do q of k minus 2? Why do I know how to do k of... Try that again. Why do I know how to do k minus 2? Because qk minus 2, that comes out of rule of conjunctive simplification. Okay. I got 9:14. Let's regather, refocus. Let's play a little game. It's called Guess the Number. I'm going to write out some numbers and you tell me which one comes next. Okay. 1, 2, 3, 4. What number comes next? 5. There we go. We got it. Good. And what's the rule we're following here? What is my nth number? First number is 1, second number is 2, third number is 3. What is my nth number? My nth number is going to be n. Only n plus 1 if I'm starting from 0. So if you're a computer programmer, then n plus 1 makes a lot of sense. But here, first number, a sub 1 is 1, a sub 2 is 2, a sub 3 is 3, so a sub n is n. So, okay, let's do another round. 1, 4, 9, 16, what? 21, 25, another 25. Lots of 25s. Okay, so there's a suggestion of 25. If we go with 25, what's our rule? What does a sub n equal to? Yeah, good. A sub n, our rule can be just square n. Okay, let's do another one. 1, 3, 7. 15, 31, 63. What comes next? This one seems a little bit harder. We got 127 as a possible answer. Got a couple of 127s. So what rule are we following if we put 127 here? So I see a 2n plus 1 in chat. But 2n plus 1 isn't quite the right idea, right? Because if n is 1, then 2 times n is 2 plus 1 is 3. And if I look at 3, 2 times 3, that one works. But if I go up here, 2 times 4 is 8 plus 1 is 9. So I don't think you mean 2n plus 1. I think you mean double the last number and add 1. So I think what you're going for is, how do I get my current value? I want to double the number that came before it and add 1 to that. If I take the previous number, I take 1, I double 1 and add 1, I get 3. I double 3 and add 1, I get 7. I double 7 and add 1, I get 15. So this is what we call a recursive sequence. Try writing that again. Recursive sequence. Whereas these are explicit sequences. Now I cheated a little bit because I wanted the lecture to go the way I wanted it to. This explicit sequence we can also write as a recursive sequence. So as was mentioned in the chat, a sub n equals n tells you exactly how to get each term. If you want the nth term, it's n. But I could also say, take the previous term and add 1. So how do I get from 1 to 2? Add 1. How do I get from 2 to 3? Add 1. Now, there's a bit of a drawback to recursive sequences. Because if I want to know what a sub 100 is, if I'm using a recursive sequence, a sub 100 is 1 plus a sub 99. And a sub 99 is 1 plus a sub 98. And a sub 98 is 1 plus a sub 97. And I got to figure out every number all the way up to 100 in order to figure out what a sub 100 is. But what is a sub 100? It's just 100. People putting the answer in the chat right now, they didn't say, well, it's 1 plus a sub 99. What's a sub 99? Well, it's 1 plus... They didn't do all that work. All they did was plug into the formula 100. So explicit formulas are nice. Because if I wanted to know, in this case, what's a sub 100, if I'm using this recursive sequence, I have to figure out everything that comes before. So there was another suggestion in chat. There was, what about a sub n is equal to 2 to the n minus 1? I think. I'm going to go with that one because that's the one that works. So are these two the same? Let's give this a different name. Let's call it b sub n. So question, is this the explicit formula that matches this recursive formula? Does 2 to the n minus 1 match a sub n equals 2 a sub n minus 1 plus 1? So here we have an example where an explicit formula, a sub n equals n, matches a recursive formula, a sub n equals a sub n minus 1 plus 1. And so it would be really nice to know, can I just use this explicit formula, this closed form formula, so I don't have to worry about recursion? And we can prove that using induction. So let's say a sub n is equal to twice the previous term plus 1 for n at least 2, and a sub 1 is equal to 1. That's important. And b sub n is equal to 2 to the n minus 1. I want to show that a sub n is always equal to b sub n. Now, there are some very confident people in chat that say, yeah, it works. I'm convinced. I tried it. I tried it for n is 1, 2, 3, 4, 5. It worked. But how do you know it's always going to work? How do you know that this doesn't break at n equals 472,947,811,412? Maybe that's the first time it doesn't work. So in order to be sure that it always works, we're going to prove it with induction. So here's my claim. I'll leave this up here. Claim for all n greater than or equal to 1, a sub n is equal to b sub n. Here's my proof. Let S of n be the statement that a sub n is equal to b sub n. Let me do a base case. S of 1 is true because a sub n is equal to 1, and 1 is equal to 2 to the 1 minus 1, which is equal to b sub n. All right, let's go to my induction hypothesis. Now, the induction hypothesis isn't free anymore. We need to stop and think. Do I want to use PMI or SMI, regular induction or strong induction? There's no cost to using strong induction. If you just want to always use strong induction, that's fine. But it is a little bit more to write, and I am very lazy. So if I can get away without writing everything, I'll try and do that. So let me think ahead, try and guess what's going to happen. When I look at a sub k plus 1, what I have is a recursive formula that only goes back one step. So is there an a sub 0? Good question. I'm starting all of my sequences at 1 in this case. Just makes my life easier. I'm only worried about a sub 1, a sub 2, a sub 3. You can start your sequences at 0 if you prefer, if that makes you happier. But I'm indexing from 1. A of n does not do a of 0 because I'm only claiming this is true for a of n greater than or equal to 1. So there is no 0. If I started my sequence with 0, then 2 to the 0 minus 1 would be 0. Okay, so for my induction hypothesis, I'm claiming I can just do normal induction in this case. So I'm going to let k be greater than or equal to 1 and assume p of k. Induction step. There's a question in chat that I don't have an answer for, so hopefully somebody can message them privately if they want to help with that. So, okay, I want to show S. My mistake. Assume S of k. I want to show S of k plus 1. So let's look at A sub k plus 1. And I only know one thing about A of k plus 1, and that's to use the recursive definition. So A of k plus 1 is equal to twice A sub k plus 1. That's using my recursive definition for my recursive formula. And now, the nice thing about recursive formulas is my A of k has appeared. So S of k says that A sub k is equal to B sub k. So I know by induction hypothesis that this is equal to 2B sub k plus 1. And B sub k, the whole point of B sub k is that it's explicit. I have a nice formula for it. B sub k is equal to 2 to the k minus 1. That's my definition of B sub k. So now I can go ahead and multiply through. 2 times 2 to the k is 2 to the k plus 1, minus 2 plus 1. Get the minus 2 by distributing, and this comes out to be 2 to the k plus 1 minus 1. And this is equal to what I get if I plug k plus 1 into my formula for B. So S of k implies S of k plus 1. And for all n greater than or equal to 1, S of n holds. So I've proved by PMI, regular induction, didn't need strong induction in this case, that yes, this is the closed form formula. It works for every n. I did it by induction, now I'm sure. Okay. Let's do another example. Give you another recursive formula. If PMI doesn't work out, I would go try SMI instead. Exactly right. Which is going to come up here. So here's a different example. This time I'll make people happy. I'll start at 0. D sub 0 is 0. D sub 1 is 1. D sub 2 is 2. And once I get above 2, for all n at least 3, d sub n is equal to negative d sub n minus 1 plus 4 d sub n minus 2 plus 4 d sub n minus 3. Okay, this is also a recursive formula. We can work out some of the values. So here's n, here's d sub n. I know 0, 1, and 2. 0 is 0, 1 is 1, 2 is 2. Oh, sorry. I don't want 2 to be 2. I want 2 to be 1. Otherwise, it's going to make my life harder. Change that here as well. Just checking my notes. Okay, and now I can work out some more values. What's d sub 3? D sub 3 is negative my last value, so negative 1, plus 4 times the value before that. So plus 4, negative 1 plus 4 is 3. Plus 4 times the number before that, 4 times 0 is 0. So 3 plus 0 is 3. So when I plug in 3, I get out 3. If I plug in 4, d sub 4 is negative my last value, minus 3, plus 4 times the value before that. Negative 3 plus 4 is 1. Plus 4 times the value before that. 4 times 1 is 4. 1 plus 4 is 5. So I plug in 4, I get out 5. And here's my claim. For all n greater than or equal to 0, d sub n is equal to, there's a closed form formula, 2 to the n plus negative 1, the n plus 1, all divided by 3. So we can check that that works for the values I've calculated so far. Plug in 0. 2 to the 0 is 1. Negative 1 to the 1 is negative 1. 1 plus negative 1 is 0. 0 over 3 is 0. That checks out. Let's just try 3 for something different. 2 to the 3 is 8. 3 plus 1 is 4. Negative 1 to the 4 is 1. 8 plus 1 is 9. 9 divided by 3 is 3. That matches. So it's looking good. But again, I'm worried about 47,974,832,412. I want to prove it's true for all n. And the only way I have of doing that is induction. So let's prove this. Let me go back to P of n, make my life easier. Let's let P of n be the statement that d sub n is equal to 2 to the n plus negative 1 to the n plus 1, all divided by 3. Okay. Well, when it comes time to do my base case, I can say P of 0 is true because 0 is equal to 2 to the 0 plus negative 1 to the 1 divided by 3. But I'm going to need more than just P of 0 because my recursive statement doesn't kick in until n is at least 3. So I also need to prove P of 1. P of 1 is true because 1 is equal to 2 to the 1 plus negative 1 squared divided by 3. 2 plus 1 is 3 divided by 3. And I need P of 2. P of 2 is true because 1 is also equal to 2 squared plus negative 1 cubed over 3. That's 4 minus 1 divided by 3. Okay, so now I come to my induction hypothesis. And let me think again. Let me think ahead again. Do I want to use regular induction or strong induction? Is it going to be enough to just know one step back? Or am I going to have to go more than one step back? What are we thinking? PMI or SMI? SMI, right? Yeah, I have more than one base case. I'm going to have to go back more than one step. So SMI makes sense here. So I'll say let k be greater than or equal to 3. Greater than or equal to 2. Not 3. K be greater than or equal to 2. I want to do my last base case. And assume P of 0 and P of 1 and all the way up to P of k. Since I'm using strong mathematical induction, I get to assume all of these things. Okay. So now I come to my induction step. And what I'm interested in is d of k plus 1. And what is d of k plus 1 equal to? It's the first thing I write here. It's not equal to d of k plus 1. So that's not how my recursive formula works. My recursive formula is up here. Which of these two statements can I use? The top one. I need to use my recursive formula. Remember, this is what I'm trying to prove. So don't make the mistake of saying, this is equal to this. No, we don't know that yet. That's what we're trying to prove. What I know is I know the recursive formula. So I can write d of k plus 1 is equal to negative d of k plus 4 d of k minus 1 plus 4 d of k minus 2. Right? That's my formula here when I plug in k plus 1. K plus 1 minus 1 is k. K plus 1 minus 2 is k minus 1. K plus 1 minus 3 is k minus 2. Okay? And I can do this, by the way. This only works if the number you're plugging in is at least 3. K plus 1 is greater than or equal to 3 because k was greater than or equal to 2. Right? Here I assumed k was greater than or equal to 2. So I get that. Okay. Now what do I want to do next? How do I move forward from here? Really good. Very, very good. K, k minus 1, and k minus 2 are all covered in my induction hypothesis. So I'm allowed to use this formula for those. Can't use it for k plus 1, because I don't know if that's true yet. But I can use it back here. So by my induction hypothesis, this is equal to negative 2 to the k plus negative 1 to the k plus 1, all divided by 3, plus 4 times 2 to the k minus 1, plus negative 1 to the k, all divided by 3, plus 4 times 2 to the k, plus negative 1 to the k minus 1, all divided by 3. And all of this is true by my induction hypothesis. Strong mathematical induction says I get to assume a lot of things, and I'm using many of those things here. And from here, it's just some algebra. I factor out a 1/3, and I get negative 2 to the k minus, so this is going to become plus negative 1 to the k plus 2, plus 4 times 2 to the k minus 1, plus 4 times negative 1 to the k, plus 4 times 2 to the k, this should be a minus 2. 4 times 2 to the k minus 2, plus 4 times negative 1 to the k minus 1. Let's close that in there. And now let's just do some arithmetic. So 4 times 2 to the k minus 1 is 2 to the k plus 1. 4 times 2 to the k minus 2 is 2 to the k. So I get minus 2 to the k plus negative 1 to the k plus 2 plus 2 to the k plus 1 plus 4 times negative 1 to the k plus 2 to the k plus 4 times negative 1 to the k minus 1. And I get some nice cancellation here. Minus 2 to the k and plus 2 to the k cancel. And I don't know if k is even or odd, but I do know that negative 1 to the k is the opposite sign of negative 1 to the k minus 1. If I wanted, I could factor a minus 1 out, and this would be minus 4 times k to the minus 1 plus 4 times minus 1 to the k minus 1. So these cancel out as well. So what I'm left with is 2 to the k plus 1 plus negative 1 to the k plus 2, all divided by 3. And this matches my formula if I plugged in k plus 1. So therefore, assuming p of 0 and p of 1 and all the way up to p of k, all of these together implied p of k plus 1. So by strong mathematical induction, for all n greater than or equal to 0, d sub n is equal to 2 to the n plus negative 1 to the n plus 1, all divided by 3. I have proven my statement holds for all n. Okay, questions about that example or anything else today? We have 1 more minute in class. I'm not going to start another problem with 1 minute left, but people have questions. Otherwise, I will see everybody on Thursday. And so this pretty much wraps up section 1 of theorems and definitions. So we'll start talking about set theory next time. That integral looks good. Will this make more sense with practice? I hope so. It was hard for me when I started, and now it makes sense to me. So it was probably practice. Can I go over the cancellation of 4 to the 4 negative 1? Yeah, so if I factor out a minus 1 here, this is 4 times minus 1 times minus 1 to the k minus 1, which is negative 4 times negative 1 to the k minus 1. So I have a plus 4 negative 1 to the k minus 1, and this is minus 4 minus 1 to the k minus 1. So those cancel. Next week's test covered Thursday material as well. Where is the cutoff? I don't know. We have not finalized the test yet. We will make an announcement on UMLearn at least before the weekend. I don't remember if there's any set theory on the test. Okay, I've got 9:45. I'll hang out for another couple minutes in case anyone has questions, but I'll stop the recording here. And yep, have a good Tuesday. See everybody on Thursday.